Next thing I want to talk about is what happens whenever you aren't near the Earth's surface. And because you're not near the Earth's surface, you can assume that the acceleration of gravity is 9.81. Then we have to deal with Newton's universal gravitation law. And here's the equation for the force of gravity if you are further away, or you should be able to say the force of gravity between any two masses. Because the force of gravity is equal to a constant, this is the universal gravitation constant here, 6.7, that is not a negative sign. 6.7 times 10 to the negative 11th, and there's the units, newtons meters squared per kilogram squared. So that's just a constant that you have to plug in there. But force of gravity is directly proportional to the two masses getting multiplied together. Notice they're in the numerator, and inversely proportional to the distance between the masses squared, and then that constant in there fixes things for us to where it all mathematically works out. So notice now, if the masses increase, you're going to have more gravity. So if M1 or M2 goes up, you're going to have more gravity, which makes sense. Bigger objects are going to pull on each other heavier. If we had one planet and then the planet got bigger, we're going to have more gravity. Also, the further away you get, notice radius is in the denominator, the further away you get, so if you increase the distance, the weaker gravity gets. But notice that's squared there. That means that how far away you are is going to be more important because it's not just divided by the radius, it's divided by the radius squared. R is going to have or the distance away, R, radius, how far away you are, is going to have a bigger playing factor. It's going to play a bigger factor in all of the calculations. Something else of note is we're always going to what's called the center of mass whenever we're measuring radius, the very center of the objects, not the edges of the objects. Now let's kind of do a plug-chug example problem. I have here the Earth and the Moon, obviously not drawn to scale. The average distance, because technically the Moon isn't a perfect circle in its orbit around the Earth, but the average distance between the Earth and the Moon is around 384,400 kilometers. And here's the mass of the Earth and the Moon, and my question is how much force does the Earth exert on the Moon? And this would be a good time to point out that's the exact same amount of force as the Moon exerts on the Earth. Newton's third law, for every force there's an equal and opposite force, right? So those two forces are the same, always pointing inwards with gravity, are always pointing towards each other with gravity. But the reason why you don't see the Earth move as much is check out the Earth's mass compared to the Moon's mass. It is times 10 to the 24 for Earth, times 10 to the 22nd for the Moon. The Earth is 2 orders of magnitude greater than the Moon. So the Moon, while it does have some influence on the Earth, so the Earth will get pulled a little bit this way and a little bit back the other way as the Moon orbits, it's very, very minor to where it really is incalculable or negligible. We don't even have to worry about it. So what is this force? How much force does the Earth exert on the Moon, and of course, vice versa? Well, we have to go back to the universal gravitation equation, so I'm going to rewrite my equation, then I'm going to substitute in numbers. Here is my radius, here is the Earth's mass, here is the Moon's mass. Now, it doesn't matter what you choose to be M1, M2. I'm going to choose the Earth to be M1, and I'm going to choose the Moon to be M2. Alright, so I substituted in all my numbers. Notice also, though, that this was in kilometers, and so I converted. I jumped the decimal 3 spots to the right, or that's also the same thing as tacking on a times 10 to the positive third there, because that's what kilo means, times 10 to the third, or jump it 3 spots to the right. So I have my G, M1, M2, I called M1 Earth, and there's my radius squared. And of course, I come out with a very, very large force of 1.99 times 10 to the 20th newtons. By the way, it'd be good to learn about the EE button. If you haven't learned about that yet, the EE on your calculator is it stands for times 10 to the. So you don't have to actually type in times 10 to the negative 11th, times 10 to the 24th over and over. You just hit EE negative 11. So if you haven't figured that out in your calculator, make sure to ask about it in class. That'll make your life a little bit easier. So force of gravity between Earth and Moon, somewhere around 1.99 times 10 to the 20th newtons. A very large force, and that's going to obviously be needed to cause the Moon to orbit around. Now, in this plug-chug problem, I actually solve for the force of gravity, but it's not uncommon to solve for the radius, right? You would need to multiply whatever that radius is over and divide by force of gravity and square root, but it's not uncommon to have to work this problem around for many other things. So don't be surprised if you have to solve for the radius or solve for one of the masses. Now, I feel pretty good about us being able to plug-chug through different problems where I have to solve for radius. I give you the force of gravity and the two masses and make you solve for radius, or I give you force of gravity, radius, and one mass, make you solve for the other. But I want to talk about these type of problems because these, if you haven't ever done them, are a little peculiar, where you actually have to figure out kind of what-if scenarios. You don't know any numbers. You just ask, hey, what might happen, or what's going to happen to the force of gravity if one of the masses, M1 here, triples. So if the mass triples, whenever you're working one of these problems, what you do, and there are a lot of ways to do it, but I think the easiest way for us right now is to replace over on this side of the equation everything that isn't being multiplied by 2, 5, whatever else with a 1. So the g would be times 1, m1 is going to be times 3, m2 stays the same 1, and r stays the same 1, and let's see what happens to the force of gravity. So I substituted in 1s for the things that weren't changing, right? The gravitational constant isn't changing, so I substituted in 1. I'm trying to figure out how many more times the force of gravity is going to end up being whenever I triple the mass. I make this guy much, much bigger, triple it, times 3, right? So then I took m1 and I substituted in a times 3, or a 3 there. Note, this equal sign is actually not proper, because FG is not going to equal this, but I'm just going to leave it there for now. Instead, FG is going to be however many times this is going to work out to be. So I substituted in a 3 for M1 because we are tripling it. M2 we're leaving unchanged, so it's just a 1. And then the radius we are leaving unchanged, so we leave that a 1 as well. And whenever you obviously work that out, you'll see that Fg is going to have to be tripled as well. If you triple one of the masses, right, I multiply by 3 on one of the masses, then the force of gravity is going to go up times 3. Now that should make a lot of logical sense to you. If you triple a mass, you make one of them, let's say we made the Earth 3 times bigger, right? 3 times more massive, I should say, not bigger, that implies volume, but 3 times more massive, then the force of gravity between, let's say, the Earth and the people on it, or the Earth and the Moon, is going to go up times 3 as well. Now let's talk about what happens if you just double the radius. So we're going to make the distance between the objects, r, grow times 2. What's going to happen to the force of gravity? So in other words, maybe you move out twice the distance you already were. You were on the surface of the Earth, and then you go the same radius of the Earth up. Or you were in outer space, and you moved another distance out. So now you have doubled times 2 how far out you end up going. What happens to the force of gravity there? Now, the initial reaction whenever you do this is you say, okay, if you go twice as far out, then gravity should go down by a factor of 2. You went twice as far out, so gravity should be cut in half, 1/2. But that's not true. Notice the r squared down the bottom. So whenever I substitute in 1 for everything not changing, universal gravitation constant, I didn't change the masses in this problem, but I doubled the radius. So I substitute a 2 in there for the radius. But it's the radius squared. So if you double how far out you are, gravity doesn't get cut in half. It gets cut down by a fourth, 25% what it was. It gets multiplied by 1/4. So what you're noticing here is the radius is going to be more powerful. Notice the radius squared, so how far out you go has a larger effect in reducing gravity than increasing the mass has at increasing gravity. So here's the exact same problem, and we're just going to use the same numbers we had here. What if we tripled the mass and doubled the radius? And as you can see, note the equal sign is not proper notation because Fg doesn't equal 3/4. But as you can see, what's going to happen here is gravity, if you triple M1, you make M1 3 times as large, but you also double the radius. You go twice as far out. Gravity actually gets reduced by a factor of 3/4, 3/4. 75% gravity goes down. So, or goes down to a 75% of its original value, I should say. So, gravity ends up getting reduced even though you increase the mass more than you increased your distance, but gravity still goes down because the radius has a larger factor. So in general, these problems, whenever you're trying to figure out how much changing one thing might change the other, what's going to occur if you triple the mass, what will occur to the gravity? Substitute in 1s for everything that isn't changing, and substitute in whatever you're multiplying by, tripled means times 3, for the thing you are changing, and see what it comes out to be. This is going to say the force of gravity is tripled, and then repeat that for everything else. The other note from this, radius has a bigger effect at reducing gravity, because it's squared, than increasing the mass does in increasing gravity.